Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Around the world, access to clean and safe water remains one of humanity's most urgent challenges. Many communities, especially those in remote or resource-limited regions, still struggle with water that carries pathogens, heavy metals, or chemical pollutants. Traditional purification methods like sand filtration, conventional membranes, chlorination, or reverse osmosis can work, but they come with high costs, energy demands, maintenance needs, and byproducts. As populations grow and environmental stress increases, demand for better, more efficient water treatment becomes ever more critical. In recent years, a remarkable material has emerged as a serious contender to transform how we filter and desalinate water. Graphene, and in particular a closely related form called graphene oxide, or GO. Graphene is essentially a single layer of carbon atoms, arranged in a tight hexagonal lattice, incredibly thin yet extremely strong. When engineered correctly, graphene-based membranes can offer water filtration that is more efficient, more selective, and more sustainable than many existing approaches. I'm Drew. In this episode, we'll explore how graphene-based filtration works, what advantages it brings, and the scientific and engineering challenges that remain. We'll cover the basic science, dive into specialized aspects, examine practical deployment considerations, address limitations, and look at the future direction. By the end, you'll have a clear understanding of why many in the water engineering community see graphene as a game changer. At the heart of graphene filtration lies the unique structure of graphene itself. Pure graphene is a sheet of carbon atoms, one atom thick. Because of this extreme thinness, graphene, in principle, could allow water molecules to pass through more easily than conventional membranes, which are typically tens to hundreds of thousand nanometers thick. Graphene oxide is a related material, essentially graphene sheets that have oxygen attached. This oxygen not only changes graphene's chemistry, but allows the sheets to stack and form membranes with controlled spacing between layers. When you stack many graphene oxide sheets together, tiny channels, as scientists called nanocapillaries, form between the layers. The spacing between these sheets can be on the order of less than a nanometer, or 0.00000004 inches. Small enough to allow water molecules to slip through, while blocking larger or more complex contaminants like salts, heavy metals, or organic compounds. Because the spacing arises naturally from the stacked structure of graphene oxide, and it can be tuned chemically or thermally, engineers gain a high degree of control over which molecules get filtered and which pass through. Water transport through these nanochannels between layers is remarkably efficient. The smooth, carbon-based walls are hydrophilic, meaning that to an extent, they repel water. This is hugely beneficial in ensuring that water can get through the membrane as easily as possible by massively reducing friction that might slow it down. This allows water to flow rapidly between the layers, much faster than through other membranes that we use today. This allows comparable or much higher throughput, even with lower pressure pushing the water through the filters. Lower pressure means lower energy use, which makes the system more sustainable and cheaper to operate. Moreover, graphene-based membranes tend to be mechanically robust. Despite being built from atom-thick sheets, their layered structure distributes stress efficiently. They resist deformation under pressure and tolerate varying chemical environments much better than any current membrane technologies. And this mechanical and chemical stability is critical for real-world treatment that might involve fluctuating water quality, contaminants, and operating conditions. Because of these properties, graphene-based filters offer an attractive alternative to traditional water treatment. In principle, you can tailor them for desalination, heavy metal removal, microbial filtration, or removal of other organic contaminants, depending on how the structure is made. Some prototype systems are already being tested, ranging from small-scale filters for household or localized use up to pilot desalination or wastewater treatment plants. In certain designs, graphene oxide membranes are combined with pre-filtration steps and post-treatment, producing water safety for drinking or industrial use. Because my membranes are thin and efficient, these systems can also be more compact and easier to maintain than large-scale, high-pressure installations. That sets the stage for deeper exploration. As researchers continue to explore the potential of graphene-based water filtration, several innovative technologies are emerging to make these systems faster, more efficient, and more adaptable to real-world challenges. Firstly, controlling pore size and interlayer spacing. One of the most powerful features of graphene oxide membranes is the ability to tune the spacing between layers, and thereby tune the effective pore size that determines what passes and what gets blocked. By adjusting chemical treatments, like a reduction of the oxygen that separates layers, changing drying or compression steps, or controlling how the sheets are assembled, engineers can shift the interlayer distance by unbelievably small amounts to create unbelievable precision. This fine-tuning lets a graphene oxide membrane be optimized for different tasks. More open spacing could allow faster flow and filter out viruses and large organic materials, while tighter spacing could block salt or heavy metals. The flexibility means that a same base material can be adapted for coastal desalination, groundwater purification, or any other application. Achieving constant, stable spacing in actual operation remains a challenge, though. But progress in fabrication methods, like careful chemical reduction, control of oxidation levels, and stable manufacturing procedures, has made such control increasingly feasible. Second is the graphene reduction in biofouling. In any water treatment system, biofouling, which is the growth of bacteria, biofilms, and algae, and scaling mineral deposits, pose major obstacles. Membranes get clogged, flow rates drop, cleaning becomes necessary, and maintenance costs climb. Graphene-based membranes offer some inherent resistance because of their smooth surfaces and the chemical properties of carbon-based materials. But that's only part of the solution. Engineers enhance fouling resistance by applying special surface treatments or coatings. These can make the surface more hydrophilic or hydrophobic depending on the context. They can alter surface charge to repel microbes or particles and add chemical groups that discourage biofilm formation. By doing so, the membranes stay cleaner longer, require less frequent maintenance, and maintain stable performance over long periods of time. This anti-fouling capacity is especially valuable for decentralized or low-maintenance systems. For example, small village water filters, portable purification units for humanitarian relief, or remote off-grid installations where frequent maintenance is impractical. Hybrid graphene polymer composite membranes is another idea that's making graphene-based filters increasingly practicable. Pure graphene membranes offer fantastic filtration potential, but manufacturing large, defect-free graphene sheets at a scale remains difficult. To bridge the gap between this lab-scale potential and industrial-scale deployment, many efforts focus on hybrid membranes, combining graphene oxide with conventional polymers, whose ease of manufacturing and tangible success have already been demonstrated thoroughly. In a hybrid composite, the polymer serves as a support matrix, giving structural integrity, flexibility, and ease of manufacturing, while the graphene-based component provides the high-performance filtration function. This synergy leverages the best traits of both materials: polymer's manufacturability, plus graphene's selectivity and permeability. These components are more resistant to mechanical stress, easier to scale, and often cheaper than pure graphene membranes. They might slightly sacrifice the absolute maximum performance of a perfect graphene laminate, but offer a very practical path toward widespread use in water treatment plants or under sink units. Another big factor that makes graphene filters so promising is their energy efficiency gains, especially in desalination. One of the biggest drawbacks to traditional desalination, like reverse osmosis, is the high energy demand. Seawater requires high pressure to force through tightly woven polymer membranes that reject salt ions, meaning large pumps, robust infrastructure, and significant energy use. Graphene membranes, because of their atomic thinness and effective nanochannels, allow water to pass at lower pressures while maintaining high selectivity. This reduction in required pressure directly translates into lower energy consumption and lower cost. For coastal desalination plants, that means lower operating costs, reduced carbon footprint, and improved feasibility for renewable-powered or off-grid systems. Moreover, in regions with brackish water or slightly salty groundwater, graphene filtration could make desalination viable where traditional reverse osmosis would be far too expensive. Low-pressure operation also reduces mechanical strain on components, which could extend system lifetime and reduce maintenance. Other graphene applications are also promising, like graphene aerogels. While membranes filter by size exclusion, graphene can also be used in other forms, such as aerogels or spongy 3D structures. These aerogels can grab contaminants that are more chemically or electrically alive. Graphene aerogels have high surface area and functional groups on the graphene sheets that can attract heavy metals like lead, arsenic, or cadmium, where they could bind organic pollutants and dyes. In such a setup, contaminated water flows through the aerogel, which acts like a sponge. Pollutants stick to the internal surfaces while the water passes through. Once saturated, the aerogel can be rinsed or treated to release and safely dispose of the captured contaminants. Then it can be reused. This absorption-based approach can complement size exclusion filtration and work especially well for heavy metal removal, industrial wastewater cleanup, or treatment of contaminated groundwater. Finally, chemical contaminant removal will hugely help graphene filters come to life. In many real-world scenarios, water contamination is complex. Different places may have different pollutants. One powerful advantage of graphene-based materials is that their surface chemistry can be modified. By attaching different chemical compounds with the filter engineers, can tailor membranes or absorbents to preferentially bind or reject certain contaminants. This chemical functionalization turns graphene filtration from a one-size-fits-most solution into a customizable platform. For example, functional groups could bind heavy metals preferentially while letting harmless ions pass, or some groups could help degrade organic pollutants under light or mild chemical treatment. This adaptability means a community facing groundwater polluted by arsenic might use a different graphene filter than a coastal town battling saline intrusion. Having a high-performance graphene membrane is one thing. Building a working filtration system around it is another. Real-world deployment requires more than just a membrane. Engineers must design housings, pre-filters, pressure regulation, pumps, and sometimes post-treatment. Pre-treatment is the most important of these steps. Even a microscopic scratch or contaminant can damage a graphene membrane or reduce its lifespan significantly. Many systems use a coarse filter up front, and then send pre-filtered water through the graphene membrane, finally polish or treat that filtered water to guarantee safety. This pre-treatment means that the large contaminants like whole grains of sand won't damage the very fragile graphene filter. Because graphene membranes can operate at lower pressure, they lend themselves well to compact, decentralized systems, like under-sink filters, community water kiosks, or solar-powered treatment units in off-grid villages. Lower energy demand also makes them compatible with renewable energy sources, like solar panels or small wind turbines, which is a major advantage in places where grid power is unreliable or absent. That's another step that makes real-world deployment just one little bit closer. In larger municipal or industrial installations, graphene polymer composites or modular membrane cartridges may be used, making maintenance simpler and compatible with existing water treatment infrastructure. Again, this modular design means that we can make real-world deployment even easier. Despite all the promise, graphene-based filtration is not a silver bullet. Several hurdles remain before it becomes a global standard. Primarily, manufacturing. Producing high-quality, defect-free graphene, or graphene oxide, at industrial scale is still challenging and comparatively expensive. Small defects, uneven oxidation, or inconsistent lamination can cause compromised performance. Second, stability and durability. In lab conditions, graphene membrane may perform exceptionally well, but real water sources, especially in developing regions, can vary widely in their pH, their contaminant load, and their chemical composition. Long-term exposure to unexpectedly harsh conditions could degrade the membrane or change its spacing, reducing performance or requiring more frequent replacement. Third is that biofouling we mentioned earlier. While graphene-based membranes reduce fouling better than many, they're not immune. Without proper pretreatment, biofouling removal, mineral scaling, or particulate abrasion could still degrade performance. In remote or resource-poor settings, maintaining pretreatment, cleaning, and replacement schedules might be difficult. Fourth is safety concerns. New materials often face strict regulatory scrutiny before being approved for drinking water systems. Ensuring that no graphene fragments or harmful byproducts make it to filtered water is critical. Additionally, long-term studies on health and environmental impacts are needed. Finally is cost. Even if graphene systems offer lower operating costs and better performance, upfront costs remain high. Funding, manufacturing infrastructure, supply chains, and training for maintenance are all necessary to make these systems viable at scale. Transitioning from pilot projects to widespread deployment will take time, investment, and coordination. Beyond these challenges, research and development in graphene filtration continues at a rapid pace. One promising direction is hybrid systems that combine graphene membranes with aerogels or other materials, creating multi-step filters that can handle a broader range of contaminants in a single unit. For instance, a community water place could use a graphene oxide membrane for basic filtration, an aerogel filter for heavy metals, and another type of coating to degrade persistent chemical pollutants. Another important frontier is scalability in manufacturing. Advances in chemical methods to produce graphene oxide at scale are happening fast. Improvements in lamination and membrane fabrication and better quality control are making large-scale production more feasible. As the cost drops, and it is, adoption in municipal systems, rural water supplies, and portable solutions becomes realistic. Researchers are also exploring the integration of sensing and smart controls. Because graphene is conductive and very chemically active, it's possible to embed sensors in the water filtration modules that will monitor the water quality in real time. It could alert operators when maintenance or replacement is needed. This is a kind of smart filtration that could reduce waste, prevent contamination, and optimize performance over time. There's also active investigation into functionalizing graphene surfaces to target emerging contaminants. By customizing surface chemistry, graphene-based filters could become a versatile platform tailored to local water challenges. In conclusion, graphene-based filtration remains one of the most promising advances in water treatment technology. Its unique physical and chemical attributes, atomic thinness, high permeability, tunable selectivity, and mechanical strength give it the potential to outperform many traditional methods. Whether filtering contaminated groundwater, desalinating seawater, or treating industrial wastewater, graphene membranes offer advantages in efficiency, energy consumption, and scalability. That said, the path from lab to global deployment has challenges. Manufacturing at scale, durability under real conditions, maintenance needs, and regulatory approval are all big problems. But the progress over recent years suggests momentum is growing. If engineers, governments, and most importantly communities invest in developing and deploying graphene filtration thoughtfully, this technology could help bring clean water to materials or to places that have lacked it for generations. In a world where fresh water is increasingly scarce, graphene may help bridge the gap between human need and technological possibility. This could mean less reliance on expensive, energy-intensive treatment. Could mean healthier drinking water and a sustainable foundation for growth. Graphene filtration offers a fertile ground for innovation. Refining membranes, functionalizing surfaces, combining filtration with smart sensing, and designing flexible systems for diverse contexts could change the world. Ultimately, clean water is not just a resource. It's a foundation for health. And graphene-based filtration doesn't promise to solve every water problem, but it offers one of the most significantly promising, scalable, and forward-looking tools that can help develop that foundation for help.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.